in this the 11 o'clock class than I did in this one. So what I'm going to do is I'm just going to keep sort of going back and forth. I go as far as I can in this class. It'll be a little bit slower because I'm writing. Then normally what I do is I just read what I wrote in this class, which goes faster. So then I write the second half in that one, and then I'll read that here and vice versa. So that'll give both classes about the same pace, where there's a good amount of writing, which goes slower. Obviously, I need time to write. And then a portion where it goes a little bit more quickly. So this is the example that we did at the beginning of that class last time. Okay. Sorry, I'm trying to do two things at once here. Yeah, it won't let me. I was originally going to try to just record the notes directly from the iPad. Someone brought this up with me last time. Unfortunately, when you're doing the Apple TV thing, the screen record button doesn't work. Okay. So this is, well, cycling back for 1 second. Last time, what did we talk about? Very briefly. We talked about the beginning of electric circuits. What is voltage? What is current? Resistance, Ohm's law, etc., etc. Then we went and talked about KVL and KCL. Can anybody tell me what KCL, what relationship it describes? Yes?
The relationship between I and P when you have the overall circuit, is that describing correctly? When you're looking at the circuit as a whole, how they should add up together?
So yes, I think you're actually describing KVL, Kirchoffs Voltage Law. And so what that says, and that came from Talleyrand's theorem, which is I think what you're saying about the powers adding up, the voltages have to sum in a loop to zero. You want to give me KCL?
KCL is when all voltages entering a node is equal to all voltages exiting.
Currents. Yes, exactly. And part of this is becoming familiar with the terminology. It's hard in the beginning to know how to describe things. Saying voltage going into something is a common mistake, but right, currents are again like water. They flow in along paths. You can say current flows from node A to node B. Current flows into component X. Okay, voltage is between 2 points. It's like a measurement of like height almost, right? You wouldn't say the height going into something. You'd say the height between point A and point B, the voltage between point A and point B is X volts. Power is normally going to be discussed in terms of, right, you have two directions. You have absorbing or consuming power from the system, okay, or you have injecting power into the system. And in both cases, that's ultimately describing a conversion, right, between electric power into some other type of power, whatever, depending on what component it is that you're talking about. But we'll become more familiar with that terminology as time goes on. So I think the best way to go about it is just use whatever language you feel kind of works, and I will try to correct as needed. All right, so we talked about KCL, KVL, thank you for those descriptions, and then moved on to Talleyrand's theorem. And Talleyrand's theorem just simply it's really related to conservation of energy, conservation of power, just says that all the power within a system needs to sum to zero, right? The amount injected and the amount absorbed needs to sum to zero. All right, so now, example 1.6 is from the textbook, and it asks us to calculate the power being dissipated by a system. Sorry, if I do that, it rotates. Okay, so they give us a circuit that looks like this. It has, what, 6 different components in it? 2 voltage sources, 4 passive components, which are just represented by these blocks. And they ask us to essentially check to make sure that this is physically realizable, that Telegon's theorem applies. And they give us the voltages as well as the currents for the entire system. They tell us 12 volts across element 3, 8 volts across element 4, etc., etc. Okay, so the first thing we're going to do is make sure we have all the values, because, right, we do need all the values in order to solve this. We haven't gotten to the part where we're calculating or solving for the currents or the voltages. Next thing that we're going to want to do is make sure everything is properly labeled and obeys the passive sign convention. Because right now we're sort of, we are very reliant on the passive sign convention to make sure that our use of Ohm's law and similar other equations is implemented correctly. Okay. So if we look at this circuit here, we'll see that passive sign convention applies for pretty much all of these. 1 amp flowing from positive to negative, 2 amps flowing from positive to negative, 1 amp flowing from positive to negative, positive to negative, positive to negative. The one place where that didn't apply, you'll see here, was for the 24 volt source, where originally it was labeled as 3 amps going negative to positive. But that's very easy to fix because we know we flip the direction. It's just a referential direction anyway. And then we flip the sign and it's the exact same thing. So what I did was I drew a new arrow going from positive to negative, and now the value for that is negative 3 amps. So even if something doesn't obey the passive sign convention, it's very easy to make it obey the passive sign convention. Because in the end, right, these directions are only references. Moving in one direction, 3 amps is the same as other direction, negative 3 amps. Next, what we want to do is we want to calculate the power dissipated by each of the elements. And so we simply just use P equals VI. And so all those calculations you can see are here. So for the 24 volt source, it's 24 volts times negative 3 amps. That gives us negative 72 watts. So the negative, what does that mean? Yes? Power is being injected, right? Passive sign convention plus our use of Ohm's law and P equals VI. The positive always refers to consuming or absorbing energy from the system. So negative means injecting it. The rest of them are positive. 16 times 1, 4 times 1. I mean, I don't think you need me to go through all the details of multiplication. Anyway, you add them all together, and these add up to 72 watts, and so it works out nicely. This is actually one thing that you can do when you get into more complicated problems to check to see if you solved it correctly, right? Because a problem, you use nodal or mesh analysis, which we'll talk about later, to solve. You get to a solution. If Telegon's theorem doesn't apply, then you have a problem with your solution. Okay, this is another example. Example 1.8. Again, from the textbook. It asks us to calculate and sketch the current and power absorbed by this device. So the picture is very simple. It's just 12 volt source with some sort of current flowing into a big box. All right? And it's intentionally vague because we're not going to be using any load relationship to describe it. What we are going to do is just take this green line here. So the green line is given to us. And essentially, it does describe the charge contained within the device at time 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I guess it's in seconds. It could be in whatever units. All right. So we want to calculate the current flow. In order to do that, what I did was I created a table with the charges and the times, again 0 through 10. And we know that current is the rate of change of charge with respect to time. Okay? So all we need to do, and this is a discrete problem because we're talking about discrete steps in time. So instead of dv or dq dt, we're going to be say delta q, delta t. And we have to calculate what those values are. So from step 0 to 1, we have no change in the charge. And so we know the current will be 0. From 1 to 2, we have an increase in the charge, which we know means that our current will be positive. The charge increases from 3 to 3 from 1 over a period of 1 second. So 3 minus 1 divided by 1 gives us 2 amps. From 2 to 3, there's no change in the charge, which means, again, the current will be 0. From 3 to 5, all right, because we have this line here that has the same slope from 3 to 5, we see a change of -3 to -2 over a period of 2 seconds. So here, -2 minus a +3 divided by 2 seconds, and that gives us -5/2 amps. And essentially, all we have to do is just keep doing this down the line for the different time steps. And I graphed it. And so the purple line is the value of I. Now, I mean, this is some stuff going back to calculus, right? The reason why we have these piecewise description, the reason why the description of current is piecewise is because the description of charge is piecewise, right? If it were a continuous function, for Q, we would have a continuous relationship for I. And it also asks us to calculate the power being dissipated. I didn't graph that because it's simply just going to be 12 times whatever the purple line is, right? The voltage across the element is staying the same. It's 12 volts. So between 1 and 2, it will be consuming or absorbing 24 watts, right? Because you have 2 amps right here, 24 watts here, where whatever the values are, 5/2 times 12, yeah.
When you're saying it's described as piecewise, do you mean only in this given problem or in general?
Only in this problem.
Okay.
Yeah, this is this is just like a typical textbook problem. I mean, there's not really, in any real application, you wouldn't have.
So in the real world, there would be more.
Well, yeah, I mean, piecewise, unless you're, yeah. To make it, instead of going off on a tangent, yes, you're right. It wouldn't show up like this. Okay. And so that is where we stopped in the other class. All right, so I'm going to make a new folder for this. 2019 ENG212. All right, so now we'll move on to some new stuff. All right. All right, so next we're going to jump into resistive elements. And specifically, so I think in the very beginning, we're in chapter 2 now, so I think in the very beginning of the chapter, they review Ohm's law and P equals VI, passive sign convention, but we've already talked about all that stuff, so we can move on. One of the questions they ask is, what is a short circuit? I think we already discussed that last time as well, right? A short circuit represents a low impedance path between 2 points, which causes current to fly through the roof. Anybody remind me real quick why that could be a bad thing? Yeah.
Because it can dry equipment or people.
Yeah, or people. Yes, so very high currents. I mean, any device you use is going to have rated ranges for voltage and current, okay? And so if you go outside of that range, either your protection equipment is going to step in, meaning that a breaker will trip, a fuse will blow, or if those things don't happen, then you'll simply just burn out your component. Quick tip, when you are in ENG214 and you hear a pop and you blow out a chip, do not touch it immediately. It will give you a nasty burn. They get very hot very quickly. So give it a second or do one of those type things before you touch it. Okay. I don't think that we have to reiterate, although we maybe haven't said it specifically in this class, what is the main driver with regard to how current moves? How does current decide, not that it has any sort of, cognizance, but, how does it decide which path it takes? Physics, I think you learned about this, May.
The path of least resistance.
Path of least resistance, right. So if we have a voltage source and we have 5 different paths that connect the positive and the negative terminals, the current, not all of it will take the path of least resistance. But it'll be split up proportionally with more current flowing on the paths with lesser resistance and less current flowing on the paths with a greater resistance. Yeah.
So when you have a short circuit, did you have a material that could withstand that, or it just gets so hot so quickly it would just break?
Well, the thing about it is, short circuit is really an ideal condition. There is no such thing as a completely short circuit because there's no material with a zero resistance. So, and that's the reason why I said low impedance path as opposed to zero impedance path. And it all depends on how much current your device can handle. Let's say you have a diode that can handle 1,000 amps, right? Then that'll be able to handle a short circuit maybe if your impedance drops to 1. Okay, 1 ohm. But if your short circuit impedance drops to 1 milliohm, then your current's going to go up. I guess what I'm trying to say is, in the end, nothing can withstand an infinite amount of power. Yeah.
Ideally, in a short circuit, it would melt anything that it would be going through, or at least warp.
Yeah. Yeah. I mean, more times than not, unless you have some sort of unless that system is specifically designed to fulfill a protection, role, yeah, it's gonna burn out. Okay. So open and short circuit, what we'll call open and short circuit testing, actually will play a really important role in this class in looking at how systems react. So we've talked about short circuit. We'll quickly show that again. But what is an open circuit? So if this is our original circuit that's given to us, then so first off, for a short circuit or for an open circuit, what we're going to be changing in both cases is the load, okay? And so it's important that we're able, either we have a pre-existing understanding of which one of these is the load, or the problem tells us, or the design tells us. Now, sometimes it's not as clear-cut what is the part of the circuit that's supplying electricity or supplying a signal, and what's the part that is the load. But for a lot of these problems and for explanation purposes, we're going to try to keep them well defined, meaning we know exactly what the load is, we know exactly what the other components are. So basically, an open circuit or a short circuit, which will take us into open circuit and short circuit tests, is going to be replacing the resistor with nothing, which would be the open circuit test, and then with a short, which would be the short circuit test. And so that's going to tell us some things about the way that this circuit operates. So if we take that and we convert it to an open circuit and short circuit test, so that's our open circuit. And then our short circuit test, or our short circuit condition, will look like that. And this is where our RL should be. So what are the conditions for an open circuit case? And I'll say this for both open and short circuit. So for an open circuit, what we have is no, or I should say no / infinite, let me rewrite that, no load / infinite load impedance. When we talk about loading, a higher load means we're drawing more power from the system, means that its equivalent resistance is going to be lower. A lesser load means we're drawing less current from, or less power and current from the system, which means that the impedance will be higher. So the terminology is a little bit inverted in that way. So if I tell you, okay, take this and increase the load, that means if it's a resistor, you're going to decrease the resistance. You will have no current flow. In the loop. So this I will equal 0 here. You'll have no voltage drop. Across the series elements. Which in this case is like the 1 ohm resistor, right? So the voltage drop here will be 0. Right? Because, can anybody tell me why this voltage drop will be 0? Why do we know that right off the bat? In the back. Exactly. Voltage drop equals current times resistance. The resistance may be positive, or we may have a finite resistance, but the current is 0. It means that the voltage drop is 0. And then that also tells us that the terminal voltage is equal to the internal source voltage. So this right here is going to be Vs, and this right here is going to be Vt plus or minus. So when we have an open circuit case, no current flows across the series resistor, which means Vt is equal to Vs. Now, so open circuit testing can help us extract some information from the system. Let's say I give you a circuit, it's working, it has a load. You want to try to model it. Part of modeling it is determining what its internal voltage is. Okay, so what you do is you perform an open circuit test. You pull out the load, you simply measure the terminal behavior, and that'll tell you what the internal Vs value is. Okay, now what about for a short circuit? What are the characteristics that we expect to see? So they mirror what's above very closely. So a 0 load impedance, or what we call a short, right? We have a very high current flow. Actually, we don't have to state that. We have no voltage across output terminals. So Vt equals 0, right? Up here, we can imagine this as being our Vt. So Vt equals 0. In this case, the voltage drop across the series element will equal Vs. If you look at this circuit right here, we know that all the voltages have to sum to 0, right? KVL tells us that all the voltages in the loop must sum to 0. So therefore, this voltage must be equal to the voltage across that resistor. And lastly, So we can calculate this RS value if we know what VS is. Okay, because we can measure I at the output terminal for the short circuit. And we can say, right, I is equal to VS divided by RS. This is getting a little bit ahead. I mean, it's really just an application of Ohm's law. But we'll come back when we get to actually use this and explain this a little bit more. But to make a long story short, the open circuit and short circuit cases will come in handy, especially when we start talking about Thevenin equivalent circuits. We're going to take circuits, apply the open and short circuit test in order to essentially extract what is the internal VS and what is the internal RS. Okay. Sorry, some of them won't scroll. Okay, so next. Kirchoffs laws, and we've already introduced them, so we will not spend a lot of time going over them again. But there were a couple of concepts that we didn't spend the appropriate amount of time discussing. So what is a node? What is a branch? We used those terms last time. Does anybody remember what they meant? Either one of them, yeah.
Isn't a node like when the current kind of intersects or when it goes like a certain way?
Exactly. Let me give a more formal definition just for testing purposes and all that type of stuff. So it's a point in the circuit that has at least two adjacent branches. All right, so something like this would be a node if you had, I can't do it with my fingers, right, but if you had three, right, anytime you have more than one branch being adjacent, then it is a node. We haven't talked explicitly about what is a branch. And that is a segment of the circuit with a non-zero voltage across it. Now, the non-zero part is not trivial. And the reason for that is, yes?
For a node, when it has at least two adjacent branches, could either of those branches be made of different materials?
Sure, most definitely. Yeah, I mean, we're really, in this course, going to keep things very much in the mathematical realm, very much in sort of the describing things by equivalent resistances, equivalent voltages. In electronics, those of you who take it next semester, that's when we get into what actually is going on behind the scenes, what materials and semiconductors and all that type of stuff. But for more or less in this course, it's going to be like resistance equals 5 ohms, and we don't really even know what might constitute it. Yes?
So in the short circuit where VT equals 0, that segment wouldn't be a branch.
This is a good question. So let's take a look back up here, and let's count the number of nodes and number of branches in these circuits. So how many branches are there in this one? There are 3 branches that have a non-zero voltage across them, or 3 lengths that have a non-zero voltage across them. This, and this. We know that there is a current flowing through the circuit. That means these will have non-zero voltages. This right here is not a branch, okay, because in these circuit diagrams, the straight line is simply just a short circuit connecting length, right? So the voltage here and here are the same, which means this is not a branch, which means these are not 2 different nodes. It means this is all one big node, okay? So you have to get used to that representation. A node is not always going to be just a single point, okay? It can be, especially the way that these circuits are drawn, often it's at the bottom of the circuit. There'll be an entire, almost like a plane, that's all like the reference plane or the ground plane, okay? So 3 branches, how many nodes? This node connects 2 adjacent branches, this node connects 2 adjacent branches, and this node connects 2 adjacent branches. Over here, how many branches do we have? Only 1, right? There's a 0 voltage across this, non-zero voltage across this, and so we have, and this is actually a branch as well because the voltage across here is non-zero. So we have 2 branches, this and this. We have 2 nodes. This is all one node connecting this branch and this branch. This is all one node connecting this branch and this branch. Over here, how many branches do we have? 2 again. This is non-zero voltage. This is a non-zero voltage. And so our nodes would be this and this. So this node actually extends all the way around and looks like that. So especially when we get to nodal and mesh analysis, we'll spend more time doing exercises like this, counting the number of nodes, counting the number of branches, highlighting them. It does play an important role because for certain types of analyses, especially when we start using matrices, the size of the matrix will be dependent on the number of nodes. And there's only one right answer. Okay, this is not one where you could say, oh, I'll call this a node, I won't call that a node. I mean, there is a right and a wrong answer. And so being able to do that housekeeping or that accounting is important to make sure that you size your matrices properly. Okay. So I'm going to draw an example that I've used before. And let's do another little exercise and count how many branches and nodes. It'll be one more opportunity for us to try this out. So this is going to be called element. Well, no. I'm not going to give that yet. All right. So let's, and I wish I had drawn this a little bit bigger, but so let's go through and let's label these. So how many branches do you see? Just throw out a number. You don't have to raise your hand. Yeah.
4, but is that box like a short circuit?
No, it's not. You can just, in this class, whenever you see a box, you can just think of it as a resistor, but it's an element that's undefined. But
5?
okay, so that would be 1, 2, 3, 4, 5. Okay. Yes. If it weren't for, and this is an intentional trick question, if it weren't for this right here. Okay. One thing which maybe we didn't make explicitly clear before is whenever you have this is a short, right? Whenever you have a short in parallel with another element, okay, all of the current is going to take this path and none is going to take this path, okay? And this is when we talk about, we use the term shorting. This short is shorting out this element right here. Okay, shorting out meaning essentially taking it out of the circuit, shorting it out. Okay, so what is going to end up happening is that here we will have current flowing, but here the current will be equal to 0, which means that the voltage across it will be equal to 0, which means that this will go away. All right? So now we have to recount our branches. So how many branches do we have? 4 branches. Okay, so let's label them. We have B1, we have B2, we have B3, and we have B4. If we do a good job of labeling the branches, then labeling the nodes will be a lot easier. Okay, and again, for all of these other elements, it's assumed that it's a non-zero voltage across it, because we have some current flowing. Okay, so what do our nodes look like? How many nodes do we have here? Yeah. 4?
Because there are those two corner nodes, and then the short itself is like one big node. Right?
Yes, exactly.
And then there's the other node between B4 and B1.
Yes, but you said the 2 corners.
No, not that one. In between B2 and B3 and B4. That, yeah. No.
This.
Yes.
Okay, so let's go from left to right. This is obviously one of them, right? Okay, so I'm going to label this. Okay, this one is another one. Now, the third node most people are thinking, right, it goes right here, right? No. Okay, so where are you saying the third node goes?
It's that entire...
Exactly. Bingo. So, there is no fourth node, because this third node right, you see the node will expand as far as there's a zero impedance path. So this whole entire thing here is node number 3. It connects 3 branches. Branch 1, branch 4, and branch 3. So we have we have 4 branches and 3 nodes. Make sense? Yes.
What
So why doesn't it short out?
Why does it only get rid of that one?
Okay, it's a good question. So, essentially, at each node, the current is being divided up, right? That's what KCL tells us. Here, right, all the current flowing in must be flowing out. Here, all the current flowing in must flow out amongst these two branches. And then here, all the current flowing in must be split amongst those two, they're not both branches, but those two paths, right? So here, the current is going to distribute and split up based on the resistances. Because it's a short, all of the current will take the path of zero resistance, and none of it will take the path that has the non-zero resistance. But you see, because we consider KCL at each node individually, this short doesn't affect this one directly, right? Because KCL is individual to each one of these nodes. So the current has to be split up between these two branches. It can't skip over and go down along that path. I mean, I'm not sure if I'm addressing the way you're looking at it. I mean, it will have an effect on the rest of the circuit. This will cause the current flowing here to get higher. It will affect the rest of the circuit. It just doesn't necessarily short out the rest of the circuit.
What if it's short, but it is possible to be like in the middle of the system?
It could be anywhere. Could be anywhere. You could draw short that looked like that. You know, short any two nodes together.
And we do the same thing.
So if I were to draw that short right there, I'll draw it in a simpler way. This short, then what would happen is you would end up with, and if you leave the other short in place, then you would essentially just end up with a circuit that looks like this. Because you will have shorted out all the elements. One short will short out that this resistor. This short will short out these two components, which in turn will short out the B4, and so you'll just end up with a shorted out source. Yes?
What happens when you change like the direction of current? Would that change the number of nodes or no?
No. It won't have any effect. So if you're doing this methodically, the first thing you can do is figure out the number of branches and the number of nodes. Okay? Then you can go and define the reference voltage names, the current directions, right? You can name them VA, VB, give them polarities, give the current directions, et cetera, et cetera. But the thing is, the number of voltages that you have to deal with will be equal to the number of nodes, right? Because we know the voltage here, 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 here is all the same voltage. So that's the reason why understanding how many nodes and how many branches there are is so important, because it determines how many values you need to solve for. All right. So this is an example from the text, and this is going to be our first attempt at trying to solve the circuit. Okay, we're not given the voltages, we're not given the currents. Well, we're given some of the voltages, but we're not given all the values right off the bat. So let's draw this. What we have is a 12-volt source in parallel, as well as series, actually, they're the same here, with this resistor. So this resistor RL equals 2 kilo ohms. I don't know if I just skipped over that one part, or we're going to talk about that terminology later, but I feel like I should probably really quick talk about this because I've been using the word over and over again. So two elements when they are in parallel. Does everybody know what that means? Parallel? I mean, it kind of explains itself, yeah?
Is that when like attach that junction?
Exactly. So the voltage across two parallel elements is going to be the same, right? These two elements are in parallel, and so the voltage across them will be VAB, plus minus, the same. Elements in series share a single node with one another. And if there's nothing else connected here, all right, then their current will be the same. Okay, so parallel elements will share the same voltage across their terminals. Series elements will share the same current flowing through them. I think at some point we go and write down the definition and everything, but I felt since I was using the terminology, we should go ahead and talk about it. Okay, so first thing is, so we're given this is essentially all they give us for this circuit. Okay, 12 volts, R equals 2 kilo ohms. I'm sure that most of you could probably eyeball this and figure out right off the top of your head, right, what's the current flowing through the system? V equals IR. So I equals V divided by R. So yeah, so it's going to be 6 milliamps because you have to worry about the 10 to the 3. But let's take a step back and talk about the method that we're going to use, because as the problems get more complicated, then you're going to need to rely on this method. Okay, so the first step is going to be count the number of nodes and branches. Okay, may not be essential to every type of problem, especially before we get to nodal and mesh analysis, but I still think it's a good thing to do just for your own understanding. Okay, so let's say we have branch 1, we have branch 2, we have node 1, and we have node 2, right? I'm going to stop drawing nodes as this really long thing because it's difficult to draw. But we're going to always just have the understanding right there. I can label a node here or I can label a node here, and it's understood that that node is going to extend to any other points that are connected by shorts. Step 2. We want to label everything according to the passive sign convention. Again, when you get further on, you don't necessarily have to use the passive sign convention every time. It's not like a hard set rule. It's just going to make it easier for us to keep our signs straight, pluses and minuses and positives and negatives. So I'll go ahead and do that. So this voltage, I'm going to give it a name. I'm going to call it VS. Its polarity looks like that. I'm going to use a different color. So VS, I'm going to call this VL plus minus. Passive sign convention tells us that this is IL and this is IS. Now I know we're labeling way more stuff than we need, right? We can already tell IL is going to be the opposite of IS, and VL is the same as VS. Okay, I get it. But again, we're applying a method to a really, really simple version of a problem. And then when this has 5 times the number of branches, you'll thank yourself for doing things in this way. All right, step 3. Is to write out all the equations that we know. Again, this is not something you're necessarily going to have to do later on. As you get a better feeling of how these types of problems work, you can pick out and say, okay, I need KVL, I need this KCL, I need this Ohm's law, and we're done. Okay, but in the beginning, it helps to write out everything that we know. So what are all the equations that we can write out for this? So we know that KVL will apply to the entire one main loop. So we know VS minus VL equals 0, right? Because the polarities of VS and VL oppose one another. We also have KCL. And KCL tells us if we apply it to node, let's say we apply it to node number 1. Node number 1, KCL tells us that the sum of all the currents entering the node must equal 0. So what are the currents entering the node? And actually, a quick, which is kind of an obvious tip, it could be the sum of all the currents entering the node or the sum of all the currents leaving the node. You can do either one. So what are the sum of all the currents leaving N1? We have IS plus IL equals 0. Now, those first 2 equations can give us results outright. So first off, VS is 12 volts, right? So we know already VL is equal to 12 volts. Okay? This will also tell us that IL is equal to negative IS. What's one other equation that we can throw up here? Yeah. Exactly. Ohm's law, right? So we're not going to apply Ohm's law to the source because that is not a valid application, but we know that that VL will be equal to IL times RL. If we flip that around, that'll tell us that IL is equal to VL divided by RL, which is 12 volts divided by 2 kilo ohms, which is 6 milliamps. Which tells us then we can feed this back up above. This is equal to 6 milliamps here. And that's essentially the first part of the solution. So the current flowing in clockwise direction is 6 milliamps. Then it asks us to also calculate the power being consumed. And this is pretty easy. PL will be equal to VL times IL. And that simply is just going to, so that'll be 12 volts times 6 times 10 to the negative 3 amps, which is, what's 12 times 6? 72? I'm not very good with that type of stuff. 72 milliwatts. And if we wanted to, we could check our answer with Taligan's theorem. It's not very hard to check in this case because we know that it's the same current and the same voltage. So this is going to be 6 milliamps times 12 volts. This is going to be negative 6 milliamps times 12 volts. So it works. You'll have negative 72 milliwatts over here, and you'll have positive 72 milliwatts on the other side. Okay.